Hello everyone, welcome to this lecture. So, now we have discussed a lot about the bivariate polynomials over a finite field. Using all those properties, we will now start discussing about how do we design a perfectly secure verifiable secret sharing. So, we will kick start with a simple setting, namely we will assume for the moment that our dealer is honest. Later on we will design a full fledged VSS on the top of this simple protocol, where the protocol will also take care of a potentially corrupt dealer. Our setting here will be n greater than 3t, which is a necessary condition for any perfectly secure verifiable secret sharing. Okay. So, as I said, we assume here an honest dealer and a full fledged VSS will be designed on the top of this. We will be working with the condition n greater than 3t. We will have a finite field whose cardinality is greater than n. There will be n distinct non-zero evaluation points from the field, which will be used in the VSS protocol. Now, what is the sharing phase protocol? So, since we are assuming the honest dealer, an honest dealer can do the following. If it has an input S which it wants to secret share, okay, which is and that element secret S is an element of field, and what the dealer can do is it can pick a random t degree bivariate polynomial f of x y whose constant term is S. For doing that, what it can do is the following. Well, there are several ways to pick this random t degree bivariate polynomial. Either it can pick all the remaining coefficients of the bivariate polynomial randomly except a constant term. That is one way of picking the random bivariate polynomial f of x y, or it can do the following. It can first pick a random t degree univariate polynomial in x whose constant term is S, the secret which it wants to secret share, as it would have done in Samir's secret sharing scheme. Okay. And then it picks t more random t degree univariate x polynomials. They are now random t degree x univariate polynomials. Their constant term could be anything. There is absolutely no restriction on these remaining t numbers of x univariate polynomials. The restriction was only on the f of x polynomial. Its constant term is supposed to be the secret of the dealer. All other constants, all other coefficients could be random. Now, it can use the Lagrange interpolation for the bivariate polynomials, and it can interpolate a t degree bivariate polynomial passing through the univariate polynomials 0 f x, alpha 1 f 1 of x, alpha 2 f 2 of x and alpha t f t of x. Namely, it can interpolate a t degree bivariate polynomial whose first row polynomial will be alpha 1, second row polynomial will be whose first row polynomial will be f 1 of x, second row polynomial will be f 2 of x, and the tth row polynomial will be f t of x, and which when evaluated at y equal to 0 would have given this f of x polynomial. Well, it is easy to see that this f of x y is a t degree bivariate polynomial. It can be also proved that this bivariate polynomial is a randomly chosen bivariate polynomial whose constant term is S. Well, its constant term is S, that is obvious, because f of x 0 will be f of x, and that means f of 0 0 will be same as f of 0, and f of 0 is S, because that is the way the dealer has chosen the polynomial. Okay. So, that is another way of picking this random bivariate polynomial. Why it is random? It can be proved very easily. So, if you want to compare it with Samir's secret sharing protocol, in the Samir's secret sharing protocol there are two ways to pick that random t degree Samir sharing polynomial. Either pick the coefficients randomly except a constant term, or fix the point 0 s on that polynomial and the remaining points select randomly. And then interpolate a univariate Summitt sharing polynomial that also will lead to a random t degree polynomial whose constant term would have been s, right. So, there are two ways to pick a random t degree univariate polynomial, either pick the coefficients randomly or pick the points randomly. The same thing we are doing even for the case of now bivariate polynomials. The dealer is supposed to pick a random t degree bivariate polynomial, except that its constant term should be the secret of the dealer. Either it can do that by picking the coefficients randomly or by picking the univariate polynomials lying on that bivariate polynomial randomly, except the polynomial at y equal to 0. Okay. That polynomial is also random, except that its constant term is the secret of the dealer. So, pictorially this is what dealer has done. Okay. Now, it is easy to see that this sharing protocol is a randomized protocol, because if the dealer wants to share the same secret s multiple times, then it will be picking random bivariate polynomials on every occasion. It will not be picking the same bivariate polynomial every time. Now, this is the way dealer will pick its sharing polynomials. Then how the shares are computed? To the ith party, the share that is given is nothing but the ith row and ith column polynomial on this bivariate polynomial, and we are following an internal dealer model here. So, dealer also will keep one share for itself depending upon what is the index of the dealer. Say for instance, if the dealer is the ith party, then it will keep the ith row and ith column polynomial with itself. The first row and the first column polynomial will be given to the first party as the share, and the nth row and the nth column will be given as the share to the nth party. That is a sharing phase protocol. Now, what will be the output of the party? The output for each party will be the ith column polynomial which it has obtained from the dealer evaluated at 0. That is actually the share, but apart from this share, the dealer has given lot of other information to the respective parties. For this, for the case of honest dealer, those auxiliary information may not be necessary, but as I said that later on we will design a full fledged VSS to deal even with a potentially corrupt dealer on top of this simple protocol. So, for the moment bear with me, do not worry that why such a lot of why so much additional information is given to every party PI, why can't it be simply given the value GI of 0 as its share. Well, if the dealer is guaranteed to be honest in the system, then we could have done that as well, but as I am saying again and again, it is not necessary that in a VSS scheme the dealer is given to be honest. We have to ensure that even a potentially corrupt dealer is following the protocol. That is why we are distributing this auxiliary information. So, even though every party PI is getting the ith row and ith column polynomial, and when I say ith row and ith column polynomial, either you can interpret that it is given the coefficients of those polynomials, and if it is given the coefficients of those polynomial, well, it can evaluate that polynomial at alpha 1, alpha 2, alpha n and get the ith row and ith column polynomial, or the dealer itself could have directly given the whole ith row and the whole ith column of this matrix as the contribution or whatever the information party PI is supposed to get. Based on that information, party PI can compute GI of y and then evaluate it at y equal to 0, and that would be considered as the share for the ith party. Okay. So, the first party pictorially you can interpret here as the following. So, the first party here will be getting this full highlighted column, and these points are nothing but the points on G1 of y then when it evaluates it at y equal to 0, then that will be the share of the first party, and like that the ith party it will have this highlighted column, the values along this highlighted column. These points are nothing but the point on g I of y, and if it evaluates at y equal to 0, it will get its share, and in the same way the nth party it will get this highlighted column from the dealer. These are nothing but the points on this column polynomial g n of y, and when evaluated at y equal to 0 will give the share s of n. Now, let us see what exactly this share S I as computed by the ith party. So, S I is the value of the ith column polynomial at y equal to 0. Now, what is the ith column polynomial? The ith column polynomial is nothing but this particular y polynomial. So, this polynomial evaluated at y equal to 0 is nothing but the value f of alpha I 0, and f of alpha I 0 is nothing but f of alpha I, because that is the way dealer has picked his polynomial f of x y and f of x. Okay. So, that means even though the value f of alpha I is not explicitly given by the dealer to the ith party, it is implicitly available, or it is implicitly given in the form of this polynomial g I of y. As soon as g I of y polynomial is given to the ith party, the ith party can evaluate that polynomial at y equal to 0, and that value is nothing but this value in blue color, and that value is nothing but this f of x polynomial evaluated at alpha I. So, in essence what party P I has done is it has computed its share as it would have got from the dealer in Samir's secret sharing protocol. In the Samir secret sharing protocol, dealer would have chosen f of x, and it would have directly given f of alpha I as the share to the ith party. Okay. The first party would have directly received f of alpha 1 as the share from the dealer, the second party would have directly received f of alpha 2 as the share, and so on. But now they are not directly given f of alpha 1, f of alpha 2 respectively, but rather g 1 of y, g 2 of y, g I of y, g n of y, which implicitly have those shares as they would have been computed in an instance of Samir secret sharing protocol. So, to what you can imagine here is that what dealer has done is dealer is running an instance of Samir secret sharing protocol internally implicitly, and it is embedding a lot of information on top of that. It is wrapping actually a lot of information on top of that Samir sharing polynomial. So, that Samir sharing polynomial f of x, which is the blue colored polynomial here, is actually embedded in a bivariate polynomial, and parties are now getting the row and column polynomials of that bivariate polynomial, and implicitly in those column polynomials the Samir shares are embedded. Okay. So, this is the sharing this is the sharing phase protocol. Now, what will be the reconstruction phase protocol? Well, every party P I can make public its share S I, and when I say broadcast, well, it is not the reliable broadcast, it is not invoking an instance of reliable broadcast, but rather sending the share over the point to point channel to every other party. So, the party P I will send its share to every other party. Okay. Even though I am using this notation or this picture of reliable broadcast, that need not be the case. Well, the parties can use instances of reliable broadcast as well to make public their shares, but that is not necessary since we are working with the setting of n greater than 3 2. Later on we will see that it is sufficient even if the parties send their shares over the point to point channels directly to everyone. So, the honest party, if P 1 is honest, for instance, it will send its share S 1 identically to everyone, but if P 1 is corrupt, it may send different versions of S 1 to different honest parties, that is fine. So, we denote the vector of shares received by all the parties as S1 prime, S2 prime, Si prime, Sn prime and so on. And what we know here is that if the party Pi is honest and whatever he has broadcasted, whatever share he has broadcasted is the correct share. So, up to T shares among these N shares could be incorrect. Okay. And the parties will not be knowing the exact identity of the T corrupt parties. So, in order to reconstruct the dealer's secret, what the party can do is the following: it can apply Reed-Solomon error correction on the received shares. Okay. So, for instance, P1 will apply the Reed-Solomon error correction, P2 also will apply Reed-Solomon error correction, Pi also will do the same. Every party will be doing locally the Reed-Solomon error correction, and after Reed-Solomon error correction, if a t degree polynomial is obtained, say f prime of x, then take the constant term of that f prime x polynomial as the output. That is the reconstructed secret. Whether that secret, reconstructed secret, is correct or incorrect, we will argue soon. So, that is a VSS scheme, and since it is a VSS scheme, it will have two protocols, one protocol for the sharing phase, one protocol for the reconstruction phase. So, the sharing phase protocol is based on distributing the row and column polynomials on a random t degree bivariate polynomial, and the reconstruction protocol is based on making the respective shares public, followed by applying the Reed-Solomon error correction. Now, let us prove the properties of this VSS scheme, whether it achieves the required properties or not, and since we are assuming an honest dealer, for simplicity we have to prove two properties, the correctness and the privacy. So, let us first prove the correctness, and just to recap, what exactly is the correctness property? The correctness property of the VSS demands that if the dealer is honest, then the shares of all the honest parties lie on some t degree polynomial chosen by the dealer, and that is exactly is happening here, because if the dealer is honest, which we are assuming to be true, then during the sharing phase every honest party Pi outputs the share S of Si, and S of I is nothing but Gi of 0, and Gi of 0 we have already shown is nothing but f of alpha I. Okay. So, there is some t degree polynomial picked by the dealer, and share of all the honest parties indeed constitute a distinct point on that t degree polynomial. And during the reconstruction phase, the value reconstructed by the honest parties we want to show is the same as the dealer's secret. So, since we are assuming that the dealer is honest, it honestly follows the protocol instructions, which ensure that during the sharing phase the share of the ith party is Gi of 0, and Gi of 0, as we have argued earlier, is nothing but the point f of alpha I is 0, and the point f of alpha I is 0 is nothing but f of alpha I, because of the way the honest dealer has chosen its polynomial. Now, imagine the t degree f of x polynomial is this polynomial, its coefficients are s, a1, a2, at. Why s? Because its constant term is supposed to be s, remaining all other coefficients are random coefficients. Now, we want to show that at the time of reconstruction, when the reconstruction phase protocol is executed, the reconstructed protocol f prime x is same as f of x, because if we show that the reconstructed polynomial f prime x is same as f of x polynomial, then that also shows that the reconstructed output s prime is same as s. Okay. So, if f of x polynomial has these coefficients, then what can we say about the vector of shares S1 to Sn held by the parties P1 to Pn, where the the entire vector is not held by P1 to Pn, the ith component is held by the ith party. Well, the collectively this vector of shares S1 to Sn corresponds to a Reed-Solomon code word for a message block consisting of the elements S, A1, A2, AT, and this follows from one of our earlier discussions we had regarding the similarity between sum secret sharing and Reed-Solomon encoding algorithm. Now, what happens during the reconstruction phase? During the reconstruction phase, there could be at most t corrupt parties who may produce incorrect shares, and we do not know what exactly is the identity, what exactly are the identity of the corrupt parties. Now, if at all we want that the reconstructed polynomial f prime x is same as the sharing polynomial f of x, this relationship should hold, which comes from the bound that we have in coding theory, namely the size of the Reed-Solomon code word minus the size of the message block should be at least 2 times the number of errors that we want to correct. Now, what is the size of the code word here? Namely, how many shares will be made public at the time of reconstruction? N number of shares, and those shares basically correspond to a Reed-Solomon code word, ideally corresponding to a message consisting of t plus 1 elements. And how many errors might be there among those n shares which are made public at the time of reconstruction? At most t shares. So, if this relationship holds, namely n minus t plus 1 greater than equal to 2 times t, then it will be guaranteed that f prime of x is same as f of x. Now, since we are working with the condition n greater than 3 t, it automatically implies that this condition holds, and which further implies that f prime of x is same as f of x. So, that shows that the correctness property holds. Now, let us prove the privacy property, and what we want to show regarding the privacy here, the privacy property of the VSS scheme demands that if the dealer is honest, then during the sharing phase the view of the adversary corrupting up to t parties excluding the dealer. Why excluding the dealer? Because we are arguing privacy only for the case when dealer is honest. If dealer is corrupt, well, in that case the secret S and the entire distribution of information is known to the adversary. So, if at all dealer is honest, we want to argue that during the sharing phase the view of the adversary should remain independent of the dealer's secret. Okay. And why only till sharing phase? Because anyhow during the reconstruction phase the secret S will be publicly reconstructed. Now, is it guaranteed in this protocol that no information about the secret S is learned during the sharing phase? So, how much information adversary learns in this sharing phase protocol? Well, it learns at most t pairs of row and column polynomials on the dealer's bivariate polynomial. And what is the dealer's bivariate polynomial? Dealer's bivariate polynomial is a random t degree bivariate polynomial with its secret being the constant term. Now, let us relate this sharing phase protocol with the BGW experiment based on bivariate polynomials which we had discussed in the last lecture. What was happening in that experiment? In that experiment also there was a secret which was the input, and to generate the output a random t degree polynomial was chosen, and the ith output consists of the ith row and ith column polynomial on that bivariate polynomial. And in the context of this experiment we had argued in the last lecture that the probability distribution of any t pairs of output row and column polynomials is independent of the input of this experiment. That means, if someone gets to see t row and column polynomials from this experiment, then from the viewpoint of that observer it could be the case that the experiment has been run with input S with the same probability with which the input would have been run with input S prime. It cannot, that observer cannot distinguish apart whether the t pairs of row and column polynomials which it has seen corresponds to input S or correspond to input S prime in the experiment, and that is why the view of that observer will remain independent of the input of the experiment. Now, what exactly is happening in this sharing phase protocol? In this sharing phase protocol we are precisely running this BGW based bivariate based experiment. What exactly is dealer doing? Dealer is basically running this experiment only, and what the adversary would have seen in this sharing phase protocol, whatever an observer would have seen in this experiment, namely t pairs of row and column polynomials. And we have already argued that any subset of t row and column polynomials from this experiment does not reveal anything about the input of the experiment. We run the same argument here and conclude that during the sharing phase, if there is an adversary with computationally unbounded resources, even in that case its probability distribution will remain independent of dealer's secret. So, well, it looks like that we have got a VSS scheme, but the answer is no. We made a strong assumption that in the VSS scheme, this simple VSS scheme, the dealer is honest. What if dealer gets corrupt during the execution of the protocol? What if he behaves maliciously? So, if the dealer gets corrupt, and remember that parties will have no idea whether during the execution of the protocol dealer is behaving maliciously or not. If the dealer behaves maliciously, then it may not follow this protocol instruction. What exactly is protocol instruction? He is supposed to pick a t degree bivariate polynomial with the secret being the constant term and distribute univariate polynomials on that bivariate polynomials to all the parties, but it may not do that, in which case what may happen is that the row and column polynomials of the honest parties may not be consistent, in the sense that may not lie on a t degree bivariate polynomials. So, what the corrupt dealer can do is it can just pick an arbitrary bivariate polynomial which may not have the degree t in x and y and distribute junk row and column polynomials to every honest party, in which case what can happen is that the share SI which every honest party pi is outputting in the protocol may not lie on a t degree Shamir sharing polynomial. Namely, the honest party pi will think that okay, I got my polynomial giy, I will just output the constant term of that polynomial, fine. So, P1 is doing that, P2 is doing that, Pi is doing that, Pn is doing that, fine. If the dealer is corrupt, then what I am claiming is that there is no single t degree f of x polynomial, there is no such f of x polynomial such that S1 is f of alpha 1, S2 is f of alpha 2 and so on. No, that is not happening if the dealer is behaving maliciously. And if this happens, that means if the shares of the honest parties do not lie on a unique t degree polynomial, then at the time of reconstruction even the error correction may fail. Parties will think that okay, their shares lie on a t degree polynomial. So, even if the corrupt parties produce incorrect shares, it is fine, we can error correct them. But at the first place, the shares of the honest parties themselves do not lie on a unique t degree polynomial. How can they think of error correcting other points? So, any polynomial can be reconstructed, it could be any f prime x and hence it could be any s prime which gets reconstructed, right. So, that is why even though the correctness and the privacy properties are achieved through this sharing and reconstruction phase protocols, if the dealer gets corrupt, then the strong commitment property of the VSS is violated, and strong commitment demands that even if the dealer is corrupt, the shares of all the honest parties should lie on a t degree univariate polynomial, t degree Shamir sharing univariate polynomial. That means, even a potentially corrupt dealer should have followed the protocol. That is why it is called verifiable secret sharing. That means, the secret sharing has been done in such a way that it is verifiable. The parties can verify that whether a potentially corrupt dealer has followed the protocol instructions correctly or not. But right now this pair of protocols is not a verifiable secret sharing, it is just a secret sharing scheme. It will work only when as long as the dealer is honest. If a dealer is allowed to be potentially corrupt, then the strong commitment property is violated. So, now in our follow up lectures we will build upon this simple pair of sharing and reconstruction protocol, and then we will develop it into a full fledged VSS protocol where even the strong commitment property is satisfied. So, these are the references used for today's lecture. Thank you.